have four days for lectures for hyperbolic equations. So you have the titles in the our colleague, but okay, I didn't respect. This is not the order. Okay, so today I will. Okay, I just say what is scheduled. So today is about introduction to hyperbolic equations, hyperbolic systems. What I want, generally, is to take the board and write. This is better, but okay, I have the microphone. So this is step one, so introduction today. Maybe half of tomorrow, I don't know, I will see about the time. When you write in the board, it's not easy to, difficult to see what is the time. I mean, if I have some more explanations. And after, we'll see what is the difficulties, etc. And after, I will talk the second step. There is three steps, okay? Second step is the scalar hyperbolic equation, okay? To see how we solve it, because to solve this kind of problem is very difficult. We know solving just a small part for systems, okay? Okay, we can do numerics, but the theory is very weak, and this is a problem. And after we come back to systems and to try to do maybe to solve some special problems for weak solutions that are called Riemann problems. So this is the three steps. I will share these three parts in the fourth seance. Okay, so today, okay, it's the first one, hyperbolic system. So we have the introduction. So there is a few parts. So first, I will give some introduction. What is the definition of hyperbolic system? After this, the notion of symmetrization, because this is what is very important. Symmetrization. And we talk what is the result. Sorry, the result about smooth solutions. And we will see that smooth solutions, generally, they exist only until some finite time, okay, even if the initial condition is very smooth. And so we need to understand what happened after. So it's not today, but the weak solutions we'll study it maybe in this part. But I will introduce the notion of entropy. Entropy pair. It's some physical property, and this physical property allows us to choose, because weak solutions we have problem existence and uniqueness, but generally we have more existence than uniqueness. And this physical property maybe allows us to select what are the good physical solutions. Not all the time, but almost. And after, we will see what happened in the linear case, and especially for the wave equations, wave equation. Okay, that's okay for the Zoom, that's fine. So what is the interest of hyperbolic systems? So hyperbolic systems describes some dynamics dynamics, and we have flows. So we have some phenomena propagating at some finite speed. This is the difference with diffusive, like parabolic equations. And diffusion give you maybe a infinite propagation. But in hyperbolic equations, you have finite propagation. So you have some phenomena here. Maybe there is, or we not have exactly the same phenomena now after a time t, but if you are very far, you have to wait then to get maybe some part of this phenomena. Okay, flows with finite speed. And the applications are for gas dynamics, for example, fluid dynamics. Okay, there is some theoretical part, but I will use examples, okay, in fluid dynamics or traffic flow. Okay, this is traffic flow. Traffic flows. But we have also waves. Okay, this is in and generally, the most, maybe there is something which is very interesting to study in this equations, is that the propagation of discontinuity, okay, and discontinuity like shock waves. Okay, we have some shock waves, etc. Shock waves, it means that you have a bomb explosion, and then you have some shock wave. You can see, so there is some photo in YouTube, for example. We can see some plane with some special thing, strange, which is shock wave. There is some discontinuity propagating at finite time. So this is very important to study in this case. Okay. So now what is the definition of hyperbolic equations? This is an introduction. So hyperbolic equation is something like this. Okay, I only say, okay, here one, and okay, it's 1D, one-dimensional, okay, every time. And even if you have system in one dimension, you have many problems. It's many open problems, okay, theoretical open problems. So, but okay, this is to understand what happened. Two-dimensional is more complicated, but there are some similar properties, okay? So what is hyperbolic equation? Say it's something like this. Yes, here, so I can put add or raise maybe transport in non-linear transport. Okay, transport non-linear. Okay. So hyperbolic systems concerns also transport, as I said, but non-linear. Okay, so have some phenomena transported, but you don't get exactly the same phenomena after time and anywhere. Okay, and plus something like this. Time of xt equals to 0. So x is in R. The time is positive, and okay, generally we try to study some Cauchy problem, initial condition, which is maybe something like this, u0 of x in R. So what is u? I put w maybe in my, okay, it's the same, but just to respect what I wrote, but it's not the system. So this is w, up. Fine. And w is a known function. So w x time is something like w1, wn, x time. Okay, so it's something living in some open space of Rn. Omega is open. generally, to avoid the problem of the boundary. Okay, and also, okay, we study here for all the set R, but we can study in some bounded domain, but there are other difficulties. Okay, you don't just put some boundary condition like Newman condition, Dirichlet condition, because you have some propagation, so you have to be careful with the boundary condition. This is a big problem also. Okay, you have some compatibility conditions to respect. So W is like this. Okay, and what is A? A is, sorry, very sorry. Yeah. Because this is, if you write it like this, it's transport equation. It depends only on x and time. But this is what is the difference between a linear transport equation is A of W. Okay, so when W change, here, this is a matrix, okay? A of W so this is a matrix of dimension R. Okay? So this is definition of, okay, we are interested in this kind of system, okay? And what is the definition of hyperbolic? Definition of hyperbolicity. We say that maybe this system, I call it S. So S is hyperbolic. S is this problem because I want to to keep my my burden at the same time keep the micro. I have only 2 hands. So is said to be hyperbolic if the matrix function A of W is diagonalizable on R. Okay, and first, okay, 1, because it's the same. And the second, which is more used, is S is said to be strictly hyperbolic if the matrix A of W has exactly n different eigen values, real, of course, different real eigen values that we classify. Okay, lambda n on W for in the domain omega in omega and also in omega. Okay, this is the definition. It means you have this hyperbolic means you have this kind of system, and because sometimes you see hyperbolic system we just write this, but after we have to say exactly what is hyperbolic, this is the condition. Okay, is it clear in the Zoom? Okay, that's fine. So we'll see that this property is a necessary condition to have that the problem, the Cauchy problem for this is well posed. Okay, this is very important. I will explain after. So there is a more interesting case because for physics generally, we have this form. So now definition. We say concept S is said to be conservative if it is written in the form, conservative form, that is something, okay, this is W. I put U or W, yes, W, that's okay. Okay, and F of WF is called the flux of the system. Okay, so in this case, this is say conservative because you write this, and in this case, what is, you can write it in the form. So here, sorry, what is A of W is the Jacobian of F. Okay. Jacobian of F. So mathematical property, if you have first your system written in this form, you cannot necessarily put it in conservative form, except maybe in one, for a scalar equation. You take the primitive of the equation, we'll see this. But in this case, you can put it in the other form. So general physical problems or models are in conservative forms. Okay, so why we say conservative? It's important. Why? We call it conservative. So it means that there is some quantity conserved in a time. So if you multiply this equation by W, okay, or W transpose, of course, and you will, sorry, no, sorry, you don't multiply. You just integrate this over the time, okay, you integrate dx on R. So what you get here, this quantity, okay, in R. So you integrate this, you will get something plus f of W the x time between minus infinity up plus infinity, okay, which is 0. So you assume that everything works, okay? You assume that if this is 0, if this is 0, okay, it means that your W at the infinity, at plus infinity and minus infinity is the same and is bounded, for example. Then necessarily this quantity is conserved in the time, okay? This is why we say system is conservative. If you have this, only this, you integrate this, not sure you get this, okay? So this is some quantity conserved. We call it generally the mass or mass density, the momentum sometimes, okay? They are physical. The most physical problems are like this, are so in form conservative. Okay. So now is symmetrization. What is symmetrization? It's two maybe. This is also an introduction. So we say that, so definition. So we say that the system, okay, in, what I forgot also. This is also important. There is, yes, also, yes, I forget also, I will not do this just after. I just want to say that if you write your system like this, or you put it in the form A of W dx of W, when you have smooth solutions, it's equivalent, okay? But when you have some weak solution like discontinuities, the problems are not equivalent, okay? So when you write it like this, or AW multiplied by WX, this is accept some discontinuity solutions. The equation with A, imagine that we are not in conservative form, AW multiplied by WX. This is a big problem. When you have continuity, you have the function A of W. Okay, so yes, this is, I remember that I have to prove something. So this problem, X, equivalent for Wx for weak solutions. So if you have some discontinuity, this quantity has a sense in the distribution sense. When you have, this is discontinuous, so it means that you have some function like Heaviside function multiplied by, so the derivative of discontinuity is something like Dirac function, and there is no good definition what is Heaviside multiplied by Dirac. Then have no sense. Okay, so be careful. Solutions, we have equivalent, so weak solutions, maybe only smooth solutions, you have equivalent. Okay, so be careful. When I write this, it means be careful. If you have your driver license, you know what is this. Okay? Equivalence. So yes, I remember what that, the property, okay, small theorem, that the property of hyperbolicity or strict hyperbolicity is independent of the change of variables. So today we concentrate on the smooth solutions. Okay, everything works. And the last, my last lecture, we will come back to see what happened for weak solutions. So this is what before we have to do what happened in scalar. Just one equation, there is many problems, and you understand what is the difficulty for systems. Okay, so let's take the proof is very easy. Okay, so sometimes, okay, because about the notations. So you remember, you have your system, and imagine that you have some change of variables. Let's U, for example, okay. P invertible is a transformation. Okay, so you change from W, you take another variable U, not necessarily linear. If it's linear, also it's easy, but not necessarily linear. So what you have here, you will get something like this. P prime, but this is the Jacobian. Du over dt plus A of W, and the W the same, I have P prime of U du over dx equals to 0. Okay. And now you multiply by p prime inversible. Yeah, p inversible like a function, and p prime like a matrix is invertible. Okay. So you multiply by the inverse of this matrix, you will get plus p prime of u minus 1 a of w p prime of u w of dx. So this is the equivalent, sorry, this is du. This is the equivalent equation for smooth solution, but with variable u. So this is maybe b of u. Okay, so you get something, the same kind of equation, hyperbolic equation. And what is nice is that A and W are similar matrix. Okay, A and W, IB, sorry, are similar. So that it means they have the same eigenvalues and they are both diagonalizable or not. And okay, they have the same eigenvalues. Okay, so this is the system with B is hyperbolic if there is it's diagonalizable, but B and A just a change of variable, change of basis. Sorry, you change the basis. The matrix don't change the properties. Okay, you have the same eigenvalues are similar. Then both both diagonalizable or not. Okay, they have exactly the same eigenvalues. Okay, fine. So this is what I forgot to say. Now I will go to the second part, which is the symmetrization. We see that the symmetrization is an equivalent notion of hyperbolicity for 1D, one dimension. Okay. So what is a definition? So we say that the system S is symmetrizable if there exists some matrix, I call it S, so now I have to change, maybe H of W, which is symmetric, positive, definite, and definite. Such that H of W multiplied by A of W, remember, is symmetric. Sorry. Okay, this is the definition. So there is a small theorem that said that if, okay, theorem S symmetrizable is equivalent that S is hyperbolic. Okay, so the proof is not difficult. I will give you some proofs that are interesting for you because they are simple. There are sometimes some theorem with the proofs, difficult proofs, so I will skip this, and you can find in an maybe I give you some references to see if you want. Maybe I will use the other part. Let's go. So this is 1, this is 2, and we prove that 1 is equivalent to 2, okay? What is the first one? I begin by 2 implies 1, okay? The reverse, okay. Well, maybe put this 1. It's not easy, so be careful. The reverse, I begin with the reverse, okay? So the system hyperbolic, so it means that the matrix A of W is something like this. So this is diagonal. This diagonal matrix and real. Okay, so your system might like this. So A of W, I put this P, W, D of W, P minus 1, G, W of dx equals to 0. And I can take, if I take the matrix, H of W will be P minus 1 W transpose. Okay. So this matrix, which is symmetric, okay, it's the same matrix, it's a transpose of this, give you exactly this one. And since this one is invertible, this one is also definite, will be definite positive, okay? Symmetric, definite, positive, okay? And if you multiply the system by H, so you get H of W multiplied by this, so this by this give the identity. So you will get P minus 1, no, sorry. HW multiplied by A of W. So if you multiply, you will get exactly this. The W P minus 1 or W. And this one, you know, this is transpose of this, and this is diagonal. So the transpose of this is exactly the same. It is symmetric. So now the reverse, the direct implication, 1 implied to 2. So it means that you have some matrix which is symmetric positive definite such that H by A is symmetric, okay? So maybe I call Okay, H of W, symmetric and definite positive, and maybe let's call C of W, which is H, which is symmetric. So in this case, you have some nice properties, algebra, okay? Algebra, so using what we call the simultaneous, maybe like this, reduction of quadratic forms when you have some symmetric definite positive and also some symmetric matrix, such that what does it mean? There exists some matrix, maybe Q of W, okay, it could depend on W, such that if you have H, W is Q of W transposed by Q of W. It means that you have some identity matrix. In this basis, the quadratic form is only x1 squared plus x2 squared plus x3 squared. This identity behind. This is algebra, okay? And for the matrix C of W, you can write it something like this. Maybe I put D, also D for the moment, because it is diagonal. And Q of W. So it means here the quadratic form, you have some diagonal, maybe alpha 1, alpha n, and it means the quadratic form is written in the form, in this basis, some basis. Alpha 1 x1 squared plus alpha 2 x2 squared, etc. Okay? This is algebra. Bilinear algebra, not linear. This property. And with this, we will see that it's easy to get that A is diagonalizable because C, you have H by A. So by AW is by QW, and then AU is H minus 1. Same. And what is H minus 1? Is Q minus 1 of W by Q minus 1 transpose. Sometimes we put it minus T. And multiplied by the same, by Q W transpose D of W and Q of W. So this is identity. Yeah. It is Q multiplied by Q minus 1, all transpose. Q by Q minus 1 is identity, same matrix. So you get then A is this one multiplied by some diagonal matrix and Q. So A is diagonalizable. Okay, so we get 1. No, sorry, 2. Okay, so Q, if you want, the matrix Q given here is here Q is P minus 1. Okay, but maybe you can see that the two properties. First, I don't use this for the equivalence. This is some nice algebra property, and you have this equivalence. Okay, and now we'll see that this notion of symmetrization is very important to prove that the problem is, so it's equivalent to hyperbolicity, to prove the existence of smooth solution until some time, finite time. Okay, I will just give you this theorem, short version, and give you why we need that the matrix is symmetric. Why this nice property? Why it is nice? Okay. So I think it's part 3, but symmetrization will be used for this, okay? So it's what is about smooth solutions. So we have some theorem that if W0 is smooth, I will say after what is here meant by smooth. It's like this guy is tall. It depends. Maybe tall here is not tall in Sweden, okay? It's a joke. If W0 is smooth, then the Cauchy problem, then the Cauchy problem means the system S plus initial condition, okay? Has a unique smooth solution on some interval like 0t start. Okay, so what t start is less than plus infinity, but generally is strictly less than plus infinity for almost cases. And what is smooth here? Smooth here means that W0 is in H2. So H2, it means that the function f, okay, here we can say function because we are at H2, it's continuous. Function, okay, maybe don't put f because f is the flux. Maybe function g, such that the integral of g2 plus g prime squared plus on r, okay, dx plus double prime squared dx is finite. Okay, this is Hilbert space H2. The second derivative, the integral is bounded. Okay. What I want to see. So the idea, well, the proof is complicated. Okay. The proof is too long, maybe. But just to say what we need, why we need the symmetrization property. So we need the symmetrization property. Just to show you, so in the simple case, okay. In the simple case, sorry. Maybe I can put it second part. So let's see just the interest that in the simple case where A is a W is some constant matrix. Doesn't depend on W, okay? So you have your system plus A. So we are in the linear case. We'll see what is the solution. In this case, it's really easy. And so A is constant. So imagine that you have H. So you multiply by H. Plus H by A. This is symmetric. And this is symmetric. Okay. This is equal to A star, A transpose, and H transpose is the same. Okay. Symmetric. And this is symmetric and definite positive. So now you multiply by W transpose. W is a vector column, okay? And by H. So you assume that W is smooth. So what happened in this case? So this one, and then you integrate. Integral. So this is exactly the one. You can write it like this. The integral of W times H W dx on R. Okay, so the derivative of this with respect to time, you will get Wt here, transpose, H W plus WTH, W transpose H, W derivative with time. But this term is symmetric. Okay. No, both, okay. I will show about this matrix. Okay, maybe I call it, remember, C. This is C here. Okay, which is symmetric. We'll see the same. Okay, so you multiply by WT by H. So you will get, and then you integrate this over R. It is WT A D W by dx. So this is here with x and this is time. I will explain why this is exactly equal to this. So if H is the identity, it's easy to understand. So this one, okay. What is, before, okay, it's the same. Okay, we'll do this, IW, X. So this is a primitive. Imagine that W is 0 at infinity. So this is 0. Okay, but maybe I need my 2 hands. So this is 0 because this is a primitive, this is the integral derivative. If W, okay, if W going to 0 at the infinity, so we use derivative of the product. So it was, we have 0 is equal to dW, oh, this means, sorry, yes, this notation, sometimes I use it, this is derivative of this with respect to x, okay? So sometimes I will use this, okay, the x, sometimes we just put this, and sometimes I put this for the notations, so sometimes I forget because it's more practical and then this one. The same for t. So the derivative of this, okay, like a product, I will first derivative of this, a w plus derivative of a is 0, a is constant, okay, dx on r. Okay, so this term is, this is a vector line. This is a matrix, and this is a column vector. So this is a real. Okay, this is a real. And the same, this is one, it's a real. So I call it alpha, for example. Okay, so alpha transpose, it's equal to alpha. A real is symmetric. Okay. So then the transpose of this so you have the projection, you have to reverse the transpose, the order. So you have WT, okay, AT, and the transpose of the transpose, the same. Okay, but this was not A, it was C. Sorry, because I multiply. This is C. A is not necessarily symmetric. If A is symmetric, it's okay. But the same, this is C, sorry. C and C. Okay. So this is C. Okay. So this one is this term, and this one is term. So this is exactly the same. Okay. So this is 0 is 2 integral of both terms, and so this is 0 because they are the same. This is 0 and the double, so this is every term is 0. If C is not symmetric, it's not the same term, or don't know, maybe this is +1, this is -1. But here the property of symmetry is important, and so what we get is this is what I proved. So this quantity multiplying this equation by W transport, this term is 0, and we get then the integral of this quantity H W dx is conserved, okay, on R. Okay, so if H is the identity, it means that you have L2 norm, but this is equivalent to the L2 norm because H is some definite matrix. Okay, so H is maybe between some positive number, not alpha, maybe small a and small b, in the sense of product, scalar product. Okay, so this is the importance. This is just to show you why we need some symmetric, the property of symmetrization, which is important. This is just to show you in the small, in the simple case, which is that is A is a constant. So we need it. The proof is long, and we need to use this. So complicated, many pages. Okay. So just to show you what is the importance of this. Okay. So we have seen this beautiful theorem, and now, okay, I said, so generally, so this is just to give you some idea of the need of symmetrization property. So about the theorem, so generally, so T star is finite. So what happened at this time? Okay, we lose smoothness of the solutions. Maybe we get some discontinuous discontinuity appears. We will see this tomorrow when we study just the one equation, scalar equation, and we can compute T star. This is important. And also, I can say. So tomorrow, okay, we will see the case, what happens at least for one equation in the scalar case. To see what are the difficulties for the systems. Even for one equation, we have some problems. Okay, that is important. This is why for today I continue to give some properties and to study what is the linear case, the solution, which is very easy. So now just I want to use some examples. Okay, this is a theoretical part, but some examples of models, because we will practice some techniques, so we need to have some real equations. Okay, so examples. The famous equation is for systems. Okay, it's Euler equations. So for fluid dynamics. So this equation is written like this: 0 of dt plus u x equals to 0. I will tell you what is rho, what is u. This is called mass conservation. P equals to 0. And another equation on this is the momentum, or the mass momentum. This is the energy. P equals to 0. So rho is the mass density of the gas. Generally, we use this for the gas, but also for the fluid, perfect fluid, because there is no viscosity. Okay, mass density. So u is the velocity. E is the energy. Sorry. G. And P is the pressure. So here W is the variable rho u, sorry, this is u, and E. Okay, this is W1, W2, W3. And if you see this part, this is the flux. So the flux is this part. F of W is rho u squared plus P, and u E plus UP. So there is a problem here because there is another variable which is P. Okay, Here, okay, this is rho u, this is W2. This is, you can write it like rho 2 U2 is W2 squared divided by rho, so divided by W1. So we have W1 and W2 here. But here we have the pressure. Okay, it's another variable. You have no equation on the pressure. So we need some closing relation. So we need that to have some equation concerning P. So P depends on the other variables. Okay, there is some for the gas, you have some beautiful formula for the pressure. Okay, so P is also a function. So if you want to derive this by with respect to rho, okay, there is some nice formula. Okay, so this is Euler equation. Okay, I will give you another one because this one in practice will take more time. I will give some one which is interesting, which is called shallow water system, and it's only a 2x2 system. Okay, so it's easier to study than 3x3. We need more time, and we have no too much time. Say called the shallow water equation. One-dimensional. Not a joke. So what is shallow water? So it means, so this is interesting for an not very deep, or yes, small deep, okay. Small deep, so you have some, so let's take the simple case, okay. This is water, like a river, but the deep is not like in the big river. Enchanted River, I think, yeah, Enchanted River, the deep is very, very big, and it's not like this, okay, just to simplify. So here you have the water, okay, this is X, and the H is the depend on X and time, okay, there is some movement, and we need also the velocity, so this is some average velocity. This is why we need that it's not so deep, so U is not the same here and here, you know, but we assume that this is small, so we can take the average. So what is the equation? So it's obtained from Euler equation by some averaging with respecting all the mathematical properties with some conditions. So it's only like this. H of u equals to 0, and plus G H2 over 2 equals to 0. So this is gravity force. Okay, here maybe if it's a gas, we don't put the gravity force, we can put it inside. This is neglected. Okay, so this is, we have two equations. So for the moment, I give you these two examples, but we will work in this for application to fluid dynamics. And for in the case of one equation, I will apply this to some traffic flow equation. Okay, we can also for one equation do something about fluid dynamics, but it's better to have two practical models, okay, interesting models. So tomorrow, half tomorrow, I will see the one-dimensional case for traffic flow. So this equation, so here W is H and HU, okay. So F of U, FW, sorry, is H of U over 2. So if you need, so be careful, if you need to write it in the non-conservative form, so if you want to write it like this, so what is A of W? So it's easy to obtain, but be careful. Our variable is not H and U, it's H and H of U. So write maybe W is something like HM, M is H by U, and the flux is, so here H of U, so it's M. Okay, so this one, you can write it H2 U2 divided by H. So it's M squared divided by H. We have to respect the variables. And plus GH2 over 2. So this is conservative form. So what is A of W? Is a Jacobian of the matrix, Jacobian matrix. So you have to differentiate this with respect to H and M. So what we get here, what we get. So here is, you have to Jacobian matrix, okay? Good, Yusuf, good. 0, yes. The variable H and M, so derivative of this with respect to H is 0. And here, 1. Good. Only 2 by 2 matrix. And here, by H. Mines, yeah, you are strong. H2 plus G is gravity, GH. And here, yes, 2. Okay, now I can put the maybe simple variable that are to simplify 0, 1. So this is M divided by H is U, okay? Minus U2 plus GH, and this is 2U. Okay, so we will try to see if the system is hyperbolic or not. So we need to see if this matrix is diagonalizable or not. What is the characteristic polynomial? PA of, so this is lambda 2 minus in front of lambda is characteristic polynomial. What I put here means you put FW minus lambda identity here, minus lambda, and you do the determinant. Comment on dit la trace, Youssef? La trace? Trace. You have the trace of the matrix here, no? Plus determinant. It's 2 by 2 matrix, okay? So here you have trace. Yeah, what is the trace? To you. It's for me, thank you. To me. To you. And the determinant is thanks. And GH, okay? So this is lambda minus u squared minus gh. Okay, so I forgot, but here, of course, we need to work on some space, which is omega, maybe h and m, such that, okay, h is the height, and there is a problem where there's no water. If h is 0, it's complicated, so just to say, okay, m is like u is in R, but h must be strictly positive, okay? So this is good, because this one is, okay, then the spectrum is, what is the spectrum? A of W. Yeah, so this is, you can write it. So this is, you can write it lambda minus u minus by lambda minus u plus. So the spectrum is lambda 1, I see u minus, u plus, yeah, if you want to get the same. Equals u plus. And this is strictly positive, okay? In omega, our physical domain, okay, this one. So we have to distinguish eigenvalues. You are in a good case, which is strictly hyperbolic system. Strictly hyperbolic system in the domain omega, of course. Okay. Just to see if we change the variables. And it will be the last. It's like in circus, you know, you have 3 balls, and now if we change, for example, if we change some with other variables that I say, for example, h and u, okay, then we will get also an equivalent form for smooth solutions with these variables, okay? So then we have, okay, so h, it's okay. So this is W1, Z1, this is Z2, if you want. And now I need an equation on U. So I need to differentiate this. So we have H plus, so it's better because I need this. Sorry, plus I have this one. HU2 plus HU. The time I differentiate this, okay, yeah, you can separate H and U2, but I separate HU and U. Okay, so I do this plus U. There are many ways to do this, and plus this term. So this is H G dH dx, it is dx, sorry. So sorry, this is dx. Okay, So I did this because I need to have 0. So this one plus this one, this is 0. Okay, because this is this equation multiplied by u. Okay, exactly this. So, and after I divide by h, so I will get e plus u x plus g dh over dx. So the second equation is, so our system is zero, and du, sorry, remember, I forget to use, but you understand the notations. D of dx, the same, if I use this, so I forgot, it means this. The du of dt plus 1/2 d of dx, 1/2 u2 plus gh equals to 0. So this is another, with this variable, we see that it's also conservative. Okay, so also we can, so maybe exercise, but not exercise, small one, sizes. Maybe you can, so this is what is B of Z, okay? It's made the Jacobian matrix of this, so it's not A, but it has the same eigenvalues. Okay, you can check this. To check this same angle, same lambda 1 and lambda 2. We have seen that similar matrix. And okay, this is good. And also, this is easy. And the second one is maybe try to, I put capital U is this variable, square root of h and u, square root of h instead of h, and try to what is the system plus maybe, I don't know, k of u to the x. And you will see that with this variable, the system is not conservative, okay? So you cannot put k of u inside the flux, okay? So this is an exercise, you can do it just to practice it, not complicated, and I think I will stop here today. Thank you very much.
Okay, let's all give another round of applause to Professor Nabil, please, on his talk on hyperbolic systems to describe flow. Do we have any questions from the participants?
Sorry for the perturbation, because you know we have to manage. It's not like slides, but okay, tomorrow we'll try to improve.
Okay, see you again tomorrow, sir, for the continuation.